welcome to Einstein Mechanics. Today we are starting with energy and general energy analysis. So it is time in thermodynamics we take the analysis of what? Energy. So throughout this episode, we are going to look at energy and energy analysis. So our objectives by the end of the lesson or at the end of this chapter, energy and energy analysis, we are going to introduce the concept of energy and define its various forms. We are going to look at the forms of energy. We are going to analyze on our systems, define the concept of heat. Remember, thermodynamics, heat power. So the concept of heat and some terminology associated with what? Energy transfer by heat. Mostly, I'm saying our analysis is going to be based on what? The heat energy. Are we good? Heat energy. We are also going to define the concept of work, including electrical work and several forms of what? Mechanical work. Now we will introduce what we call work. Are we good? When the heat energy is generated, what does it do for us? It does work. And we will talk about electrical work and some mechanical work. It's interesting. We also introduce the first law of thermodynamics, energy balances, and mechanisms of what? Energy transfer to or from a system. So this episode and the other ones, they are very interesting. Now, forms of energy. In this episode, we are talking about energy and energy analysis. So let's look at energy. Let's dive deep inside energy. Energy can exist in numerous forms such as thermal. You take note of them. We are talking about thermal energy, mechanical, kinetic, potential, electric, magnetic, chemical, and nuclear. Are we good? There are other forms of what? Energy that may exist, but we are listing a few of them here. And look at all this type of what? Energy, thermal, mechanical, kinetic, and the stuffs. And there are some constitutes the total energy of the system. So all these forms of energy combined now forms what the total energy of a system. So anytime I have a system over there, if I want to know the total energy of this system, total what? Energy of this system, it is the summation of the thermal energy in the system, the mechanical, the kinetic. In fact, combining all the energies that is what? Inside the system will give us what? The total energy. It's very simple. Are we good? So any system, total energy is the summation of all the what? Forms of energy that are available in or what? Acting on the system. The total energy of a system on a unit mass is denoted by what? E, and it's expressed as this. So the total energy of any system, the total energy is represented by capital E. So during our analysis, anytime I write E, it represents what? Total energy. And remember, the total energy is the summation of what? Chemical energy plus all the electrical plus all the magnetic and what? All the stuffs that are what? Available inside the system. It's very simple. And what we are trying to say is that E, this small e, represents what? The total energy on what? A unit mass. Remember, anytime you have a system, there are what? Masses that make up what? The system. Masses. Small masses that make up what? The complete system. So now E represents the total energy, the entire energy of the whole system. But what if I want to know the energy of this single particle? This single particle, one, two, I want to know the energy of this small, the third one. What do I do? So to know the total energy of a single or a unit mass, you have to divide the total energy by what? The mass. Are we good? So assuming this has a total energy of what? 50 kilojoule, and the total mass is what? This is 50. 50 kilojoule, and the total mass is what? 25 what? Kg. And I want to know the unit mass what? Energy. Then the unit mass or the unit energy will be what? The total energy E, which is 50 on what? The mass, 25. And I'm getting what? 2 kilojoule. Meaning for this system, each particle or each mass is what? Possessing an energy of what? 2 kilojoule. That's what it means. So E represent the total energy of what? A system on what? A unit mass. And it is denoted by what? The small e. Remember, the capital E tells what? The total energy of what? The entire system without considering the individual particles. It's interesting. Thermodynamics provide no information about the absolute value of the total what? Energy. It deals with only the change of the total energy, which is what matters in what? Engineering problems. So we'll talk about these ones in the episodes. So what is important here is that we know the total energy of a system. We will make equations out of it, but first get the understanding that the total energy of any system is the summation of all the energy energies acting within the system. And if you want to know the energy of a unit what? Mass, you divide the entire what? Total energy by what? The mass. And this is what? Quite simple. Now, the total energy of a system is grouped into two. We have two groups. We want to consider a system, and this is very simple. So first, let me have my system. This is my system. I have several particles, several masses coming to form what? My system. And we want to make energy analysis on this system. And there are two ways or two groups. What we call the macroscopic and what? The microscopic. So the macroscopic forms of energy are those a system possesses as a whole with respect to some outside reference what frame such as kinetic and potential what energies. So the macroscopic form of energy analysis is the energy possessed by the system as a whole. So if I make analysis on this whole system and I get 100 kilojoule what energy, then this energy, that's what the total energy of the system becomes what? A macroscopic what? Energy. I hope you are getting it. The energy possessed as a whole with respect to what, some outside what reference frame. So inside the system and with respect to some outside what energies that are acting, maybe potential energy and kinetic energy. When I make analysis of all of them and get my what? Energy, that form of energy is called the macroscopic what? Form. The total energy possessed by the whole system. Very simple. Remember, we talk about these things, the same thing when we were talking about how we study what thermodynamics. We saw we have the classical approach and we have what? The statistical approach. We saw the classical approach to consider the whole what? System for analysis, and this one talks about what? The single what? Particles. The same thing, the energy we are doing here. The macroscopic form talk about the entire system, the energy, and the microscopic form of energy are those related to the molecular structure of a system and the degree of the molecular what activity, and they are independent of what outside frames. So the microscopic, as micro, very small, this form of energy analysis account for each particle, the molecular what activity, the molecules, what they are doing, the energy generated by each molecule. So we make account of each molecule, the amount of energy you are contributing. And this form of energy analysis is what? The microscopic form of what? Energy. Very simple. You consider the system as a whole for macroscopic. Now you consider the degree of what the molecular activities. What is actually happening? Assuming this is what water and I apply heat to it. Now if I want to know the total energy using the microscopic form, I have to measure what or make analysis of amount of heat absorbed by each particle, each molecule. What energy are you absorbing? What are you going through? So that I can know my what? Total what? Energy. And that form of energy analysis is what? The microscopic. And with that, we don't consider what? Or it is independent of outside frames such as kinetic and potential energies. We don't make analysis of what the outside what? Energies, which is potential and kinetic energy. The sum of all the microscopic forms of energy is called the internal energy. Let this then be in your mind. The sum of all the microscopic form of what energy is called the internal energy of what a system, and it is denoted by the letter U. So we are going to be using EU. Now we know that E is what? Total energy, and we know that capital U is what? Internal energy. So what we are trying to say here is that we know the microscopic form of energy is what? The energy possessed by each molecule. And what this statement is trying to say is that when we add all these small molecules, the energy they possess, it's called the internal energy. And it's true. Remember, for the microscopic approach, we don't what? Account for what? The outside frames, because kinetic and potential energy they are what? Ignored. So we only consider the molecules inside the system. And yes, if I add the energy possessed by each particle in the system, I'm going to get the total energy within the system, which is very simple. And that internal energy possessed by each molecule to form the total energy is denoted by what? U. So U is what? Internal energy. Are we good? So in the analysis of the total energy, effect of magnetic, pay attention, electrical, and surface tension are usually ignored. I'm going to make some analysis here. We are going to meet our first equation here. In analysis of total energy, what we are saying is that anytime you are finding the total energy on a system, effect of magnetic, electric, and surface tension are usually ignored. Hence, the total energy of a system consists of the kinetic, potential, and internal what? Energies. Are we good? So I still have my container closed. So let's add some molecules. So now this container becomes what? My what? System. And what we are trying to say is that now I want to make analysis of what? Total energy. The energies what acting on this system. I want to make that analysis. And in thermodynamics, what we are saying here is that if we want to make that analysis for the total energy, the effect of magnetic, electric, and what surface tension are what? Ignored. So first, these energies are what? Ignored. So now, what energies are left? Hence, the total energy of a system consists of now the kinetic energy will count, the potential energy will count, and the internal what? Energy. Remember, both the macroscopic and the microscopic, with the macroscopic, we make use of the kinetic and the potential. And with the macroscopic too, we talk about what the internal energy. So the three are combining to give us what? The total energy. I hope it's simple. So look at our total energy, which is denoted by E, is equal to U, which is the what? Internal energy. So my entire energy acting on this system is giving us the U, which is the internal energy, the energy possessed by each particle or summation of all the energies by the molecules. That would be my U. Their summation will give me what? The internal energy U. And remember, kinetic energy and potential energy will be also acting on what? The system plus kinetic energy plus potential what? Energy. And that's the first what? Equation. Our total. So this is the first equation in our thermodynamics analysis, that anytime we want to write our total energy, our total energy is giving us the internal energy plus kinetic energy plus potential energy. We can further reduce this. We know that U is just U, internal energy plus kinetic energy. We know the formula for kinetic energy. Ke half mass times what? V square. Velocity square. So I'll bring it half mv square plus, we know potential energy is given as what? Mass times gravity times height, where z is the height. So we have mass times gravity times what? Z, height. So our internal or our total energy on a system can be written as this, as our equation 1. Are we good? And we know that E is just also what? Total energy, but per unit what? Mass. So I can just change this, that the energy per unit mass, the total energy per unit mass is given as what? Small letter E, the same formula, which is U, but small letters Ke plus what? Pe, which is the same as E is given as what? Our U, this is half V square on what? V square plus Gz. Why is it that the masses are what? Vanishing from this point? Remember, E is given as what? Capital E on what? Mass. So when you divide this through by mass, this through by mass, this through by mass to get the small e, are we good? We are going to get what? This capital U over the mass will give us a small u. Are we good? Don't say I didn't bring the mass here. This capital U, which is total internal energy, divided by the mass will give us a small u. And this small u will tell us that it is what? Specific what? Internal energy. Are we good? And this mass will cancel that, giving us half v square. This mass will give us what? Gz for that. So let these equations be in your mind. It's very simple. Internal energy plus kinetic plus potential will give us the total energy on what? A system. And if you want the one per unit mass, it is given as U plus Ke plus that. But when you are further reducing it, you have to make the analysis well and see that for the unit mass, the masses are what? Gone. Are we good? It's very simple. So most closed systems remain stationary during a process and thus experience no change in their kinetic and potential energies. We are trying to establish a point here. Pay attention. It says most of the closed systems remain stationary during a process and thus experience no change in kinetic and potential energy. You understand it? Closed systems whose velocity and elevation of the center of gravity remain constant during a process are frequently referred to as a stationary system. The change in the total energy of a stationary system is identical to the change in what? The internal energy. All this grammar is what here. See, we know that our total energy is given as what? U plus what? Ke plus Pe. Pay attention. In an analysis or in a question where we say the system is what? A closed system. Pay attention here because when you are solving question, you'll be asked or you'll be given that clue that this system is a closed system. And anytime a closed system remains stationary, we assume that there's no change in kinetic and what potential what energies. So let me have a system here. This is my system. It is closed because yes, it is closed, no mass out. And what we are trying to say is that if it is closed, then there's not going to be any change in kinetic and potential energies for the point 1. Point 2, closed system whose velocity and elevation of the center of gravity remain constant during the process are referred to as what? Stationary what? Systems. So now, if it is closed and it is stationary, remember, stationary means it does not move. Are we good? It does not what? Move. Meaning we know Ke to be, pay attention, to be half mv square, and Pe to be mg what? Z or h. So now you are telling me the system is what? Stationary, is closed, is stationary. These two words will be used. Stationary. Anytime you hear it in a analysis or a closed, you have to pay attention to the kinetic and the potential energy. So let's think about the stationary. So if a system is stationary, meaning this velocity is what? Not changing, it's not moving. We know that velocity will be what? Be change in velocity v2 minus v1. But here is the case you are telling me the system is what? Stationary. So the change in v will be what? Zero. And if the change in v is zero, meaning kinetic energy will be what? Zero. Are we good? If it is stationary, then there's no change in height, z, for the potential energy. And if the z or the height is not changing, is zero, then my potential energy is also what? Zero. And now what the third point is trying to say is that the change in the total energy now, after making this analysis of a stationary system, is identical to the change in what? Its internal energy. So if my E, now kinetic energy goes to zero and Pe goes to zero, then I can say E is equal to what? U. So anytime I have change in energy, it is the same as what? Change in what? Internal energy. It's very simple for stationary systems. That's why we say the change in the total energy of a stationary system, pay attention, not any system, stationary system, is identical to the change in the internal energy. There is it. Because kinetic went to zero, potential went to zero. So anytime you're making analysis and you hear that the system is stationary, your kinetic goes to zero, your potential goes to zero, and the total energy is equal to what? The change in what? The internal energy. Are we good? Now, let's look at our last slide for this episode. Control volumes. You start to solve questions. Control volumes typically involve fluid flow for a long period of time, and it is convenient to express the energy flow associated with a fluid stream in the rate form. I'll explain further. It's very interesting. This is done by incorporating the mass flow rate, which is the amount of mass flowing through a cross-section per unit what? Time. It is related to volume flow rate, which is the volume of a fluid flowing through a cross-section per unit time by the expression that. So now what we were talking about initially was what? Closed systems. But you know that control volume is also called what? Open system. So what about analysis on a system which is open? Open system. For example, let's assume this is a pipe, it's open. How do we make analysis? So what we are trying to say here is that anytime there is what? An open system or a control volume, there's what? A flow in. There's always a flow in and what? A flow what? Out. Control systems always have flow in and what? Flow out. Are we good? And what we are saying is that we have to know the what? The flow rate. If it is open, by what amount is a fluid entering and by what amount is a fluid what? Flowing out. So when we know that, we can make analysis of what? The energy. Are we good? We can make analysis of what? The energy. And we will assume it to be what? Fluid flowing through what? The system. And if we are making analysis, then we are going to calculate for the mass what? Flow rate. The amount of what? Substance coming out per unit time, the mass. If let's say 20 kg of water is flowing out, at what rate per unit time per second, then this will be our mass flow rate. Are we good? So for every second, we can see that 20 kilogram of what? Water will flow out. And that will be what? Our mass flow rate. And it will help us in what? Our analysis. And for fluid, our mass flow rate is given us when you have an open system, like a pipe, anything open that we have a flow. Our mass flow rate. Anytime you see a mass with a dot on top is flow rate. Our mass flow rate is given as what? The density and what? The volume, or the volume flow rate. Are we good? Or the velocity. This is about the velocity. Are we good? And we can further simplify this to our rho, the cross-section area, and what? The velocity average. It's very simple. We'll use all these equations in what? Our analysis. So the mass flow rate, we want to know mass of a flow. It is given as this of that, where AC is a cross-section what? Area. So looking at this, the cross-section area is given as what? Pi d square on what? 4, which means we are considering to be what? Circular. Are we good? So when you know the cross-section and you know the density of the fluid and the velocity at which it is flowing, it is easy to calculate the mass flow rate per second. How much or what quantity of what? The fluid is it flowing out? Are we good? And when we are done with the mass flow rate that we know, we have to account for the energy. So as it is flowing, what energy is it dissipating? So the energy, the total energy or the energy flow rate is given as the mass flow rate by what? The E. Look at this equation. It's very simple to understand. The total energy of the system is given by the mass flow rate that you calculated for, or the mass that flows per each second, multiplying what? The energy of what? Each one. So here the assumption is that we are multiplying the mass by each energy possessed by what? A molecule. And that will give us a total energy. I hope you get the understanding. The total energy of the flow or fluid that is passing through this pipe is given as the mass flow rate. That's the total mass flowing, multiplying by the energy possessed by each particle. And yes, that will give us the total what? Energy. So when it comes to open system or control volumes, where we have a flow, this is our energy analysis equation. E, flow rate. Don't forget about the flow rate, which is on top, is given by that. And our mass flow rate is also given by that average, which is also that, the cross-section area, and the velocity average. Are we good? So with this, we've gotten the understanding of what? The energy analysis equation of both closed systems and what? Control volumes. Let's get to the other episode and see what we can make out of it. Thank you.